Welcome to the Explainer. Today, we're diving into one of the most fundamental yet wildly misunderstood concepts of our everyday reality. You know, spending our whole lives anchored to this planet by gravity kind of plays a trick on our brains. It makes us mix up two totally different physical concepts, mass and weight. We toss these words around like they mean the exact same thing, but in physics, confusing mass and weight is literally like confusing the amount of water in your glass with how hard that water is pushing down on the table. So let's strip away this gravitational illusion and rebuild our understanding of the physical world from the ground up.
Let's kick things off with a simple morning routine. You stumble into the bathroom, step on your everyday bathroom scale, and look down at the numbers. What are those scales actually measuring? Most of us just naturally assume they're telling us how much stuff or matter we're made of, our mass, right? Well, I'm gonna go ahead and challenge that right now. Your bathroom scale is actually lying to you, or at least it's only telling you a very localized truth. Believe it or not, it's not measuring the amount of matter in your body at all.
Okay, let's dive into this. Picture the classic balance scale you see at the doctor's office and compare it to your regular spring-loaded bathroom scale. The doctor's scale works by comparing your body to sliding counterweights. Because gravity pulls down on both you and the weights equally, it's actually measuring your true mass. You could drag that scale to the North Pole or literally fly it to the moon, and it would give you the exact same reading. But your bathroom scale? That's just a platform measuring the downward pull of gravity compressing its internal springs. It measures the local gravitational force. If gravity shifts, your weight changes on that screen, even though you haven't lost or gained a single molecule.
Section 1. Newton, mass, force, and acceleration. Let's look at where this all started.
To really wrap our heads around this, we got to rewind over 300 years. Back in 1687, Sir Isaac Newton dropped his monumental book, Mathematical Principles of Natural Philosophy. In it, he laid out the laws of motion and totally nailed the concept of inertia. That Latin quote on the screen basically means that a change in motion is always proportional to the force applied. Newton realized that objects have this built-in resistance to changing what they're doing. That's inertia. And the measure of that inertia? That is your mass. Mass doesn't need gravity to exist. It's just the pure amount of matter, the total head count of atoms and molecules packed into an object.
This whole idea is perfectly tied together by Newton's second law. F equals ma. Force equals mass times acceleration. Honestly, it's an absolute game changer for classical mechanics. This brilliant little formula separates the constant amount of matter, that's the m for mass, from the situational pull, the F for force. Down here on Earth, gravity accelerates objects downward at roughly 9.81 meters per second squared. So if you have a 1 kilogram mass, Earth pulls it with a force of 9.81 newtons. Under standard Earth gravity, that force is exactly what we call weight. So mass is your constant, but weight? That's entirely situational.
Moving to section 2, inertia, Earth versus the moon.
Now, what's really interesting about this slide is the sheer contrast. Let's say we have a 100 kilogram object. On Earth, thanks to our local gravity, it's got a hefty weight of about 981 newtons. But take that exact same object to the moon, where gravity is about 6 times weaker, and its weight plummets to just 163 newtons. It literally weighs a fraction of what it did. But look at the mass column. It stays at exactly 100 kilograms in both places. The object didn't shrink, it didn't lose any atoms, its mass is 100% unchanged.
And because that mass is perfectly intact, its inertia is exactly the same too. Think about recoil kinetics. If you set up a pool table on the moon and smashed the cue ball into the rack, those billiard balls would scatter with the exact same speeds and horizontal energy as they would right here on Earth. Or imagine trying to push a massive transport vehicle horizontally. Getting it rolling on the moon takes the exact same energy and physical sweat as it does on Earth. Why? Because you're fighting its constant mass and its stubborn inertia, not its local weight, which, as we know, has basically vanished.
Section 3, earthly paradoxes, elevators and airplanes. Let's bring this thought experiment back down to Earth.
You know, we don't actually need to rocket off to the moon to trick our sense of weight. Picture yourself stepping into this elevator. You bring your trusty spring bathroom scale along and stand on it. Right now, the elevator is just parked. Let's say your mass is about 71 kilograms. Gravity is pulling you down and the scale is pushing back up with an equal normal force. Since there's zero acceleration right now, the scale reads your normal gravitational weight. Everything feels completely standard.
But watch what happens the second we add acceleration. Suddenly, the elevator shoots upwards. On top of gravity, the floor is now forcefully shoving into your feet to accelerate your mass. Boom! The scale jumps up. You've literally gained weight. Actually, scratch that. You've gained apparent weight. Now the elevator suddenly plummets. The floor drops away from under you. The upward force drops, and your weight on the scale plummets. You lost weight. If the cable snapped and you were in free fall, the scale would actually read 0. But through all these wild fluctuations, your mass hasn't changed by a single gram.
Which brings us to another everyday scenario that totally messes with our intuition. We just saw how acceleration changes your apparent weight, but what about buoyancy and flight? When a massive airplane takes to the sky, or when you dive into a swimming pool and float serenely on the surface, does that weight actually disappear? Has gravity just given up?
The answer is a massive no. The weight isn't gone, it's just cleverly hidden through distribution. When a jumbo jet is cruising, it's not weightless. Its wings are pressing down on the air, transferring all that immense weight across a huge area of the atmosphere, which ultimately pushes down on the Earth. Same with you in the pool. The water pushes you up, making you feel completely weightless. But if that entire pool were sitting on a giant scale, the scale would still register your full weight. Your body's weight is just distributed out and transferred to the bottom of the pool.
Section 4. Orbital weightlessness. If planes and pools are just earthly magic tricks, what about the greatest illusion of them all? I'm talking about zero gravity. You see astronauts floating effortlessly on the International Space Station, and it looks like gravity just doesn't exist there. But let me tell you, gravity is absolutely present. Up at that altitude, Earth's gravity's still pulling on them with about 90% of the force we feel on the ground. So why are they floating? Because they are in a state of continuous freefall. The ship, the astronauts, their tools, everything is endlessly falling around the curve of the Earth at breakneck speed. Because they're falling together, there's no floor to push back against their feet. Without that pushback, a scale reads 0. The weight is gone, but the gravity certainly isn't.
And this brilliantly illustrates how their mass is completely untouched by this orbital illusion. Imagine an astronaut out on a spacewalk. They feel totally weightless. If they try to gently shove a 1-ton satellite, it takes a certain amount of physical effort. But if they float over to a massive 10-ton satellite and try to push that, it's going to take exactly 10 times more effort and force to get it moving with the same acceleration. Newton's second law strikes again. Even when the sensation of weight completely vanishes in the void of freefall, the body's mass and its stubborn inertia survive perfectly intact.
Section 5. The main differences. A quick summary. Let's wrap this up.
All right, let's lock this in with a rapid-fire summary, especially if you're just getting into physics. First, mass is your constant, unchanging amount of matter. Second, weight is just a situational force totally dependent on whatever gravity you happen to be sitting in. Third, that's why a doctor's balance scale measures true mass, while your bathroom spring scale just measures the local downward pull. Fourth, Newton's F equals ma is the mathematical bridge connecting mass, force, and acceleration. And finally, whether you're floating in a pool, plunging in a broken elevator, or orbiting the Earth, your mass and your inertia remain an absolute constant everywhere in the universe.
We spend our whole lives letting the illusion of weight dictate how we feel the physical world. But now you're looking at things through the lens of classical mechanics. You can separate the situational forces from absolute matter. So considering all the unseen physics we just uncovered in this explainer, I'll leave you with this. What other invisible forces are shaping your reality and tricking your senses right at this very second? Keep asking questions, keep looking closely at the world around you, and I'll catch you next time.